This video will be on center of mass and center of mass velocity. If you take a meter stick, which is made up of a bunch of particles, and consider, for example, the gravitational force, what pulls on each of those little particles, pulling it downward. But of course, we've done this in the past where we just consider one gravitational force for the whole meter stick, and that gravitational force acts at the center of mass. So this video will be about, figuring out where the center of mass is for an object or like, collection of objects. So if you throw a ball in the air, it'll take this parabolic trajectory. And if you take that meter stick we were just talking about and you kind of just twirl it up into the air, the meter stick will rotate about its center of mass, but its center of mass will take that parabolic trajectory. Um, and so, this side of the meter stick, it might do something like this, where it kind of goes around. It'll take maybe some kind of path like that. It's just an illustration of it. But the center of mass will take this parabolic trajectory. You do the same thing with a hammer, where the center of mass would be somewhere over here. You can toss a hammer in the air, and again, the center of mass will take that trajectory, but the hammer will be rotating about that point. So the ends of the hammer will not take that shape, but kind of rotate around it. Let's figure out the center of mass for a ball glued to the end of a stick. And we have the mass and the length and radius of the stick and the sphere right here. And this is the equation for figuring out the center of mass. I think this is a more useful way of writing it up here, but you will see this on the formula sheet as this. And it means the same thing. This is the sum of each of the masses times the distance to their center of mass over the sum of all the masses. And we're going to use this top version, we're going to use it more like this. So let's go ahead and do that. The center of mass. And in our example here, we have two objects. I'll call the stick mass 1. Oh, we already did that. And the sphere will be mass 2. And before we get started, we need to specify a reference position, or, yeah, reference position. If we're going to figure out the center of mass, it's a certain distance in relation to what? We're going to say, we're going to say this is 0, position 0, and we're going to figure it out relative to that point there. So let's put this in. This is mass 1 times x1 plus mass 2 times x2 over mass 1 plus mass 2. Mass 1 is 1.2 kilograms. And, okay, x1. X1 is the distance from 0 to the center of mass of mass 1, which is the stick. And so this stick is uniform. Its center of mass is actually right in the middle of the stick. And so the distance to the middle of the stick, if the stick is length 2, this would just be 1 meter. Meter. And mass 2 is 5 kilograms. And this is where you have to really think about what it's saying here. We're not going to put in the radius here for the distance. We need to know in relation to where the 0 is, the reference, where the center of mass of the ball is. So of course it's going to be in the center of the ball, and it'll be the length of the stick plus the radius of the ball. So that's 2.15. And mass 1 plus mass 2, let's say 1.2 plus 5. And I'm going to just continue my work over here. This is 1.2 plus, let's just grab a calculator. 0.75 all over 6.2. Oh, okay, it was 1.2 plus 10 point, oh gosh, I forgot already. 10.75 all over 6.2. 1.93. Units are in meters. That is the center of mass of the ball stick. And so if the length of the stick is 2 meters, yeah, it's going to be a little bit less than the 2 meters, somewhere right here. Which should make sense. Let's keep going. Now, where's the center of mass for 3-point masses? We've set up a coordinate system, uh, mass 1, mass 2, mass 3. And this is in 2 dimensions, but we'll start with the x dimension first. This will be mass 1, x1, plus mass 2, x2, plus mass 3, x3. We'll say mass 1 plus mass 2 plus mass 3. Oh, mass 1 is 3. Its center of mass is at 2. Mass 2 is 4. And it is at, oh, sorry. Oh, no, yeah, it's 4. And you can find it at position 3, the x position, and then 7, 5. 5, 3, and 2. That's good. 3, 4, 7. Okay, great. I almost always forget to add up all the masses at the bottom. This is 3 plus 4 plus 7. So that looks like 6 plus 12 plus 35 over 14. 6, 12, 35, 14. 3.79. So that's just part of it because we need the y coordinate. So the center of mass for these objects would be 3.79, so somewhere right here. But now we need to find the y coordinate. So let's do this for y, m1, y1 plus m2, y2 plus m3, y3 over m1 plus m2 plus m3. And that would be 3 times 0. This would be 4 times 2. And this would be 5 times 1. Ah, sorry, 7 times 1. Uh, 3, 4, 7, have those in there right. And then 0, 2, and 1. Okay, get that right. And they're going to add up to 14 again. The mass is 3, 4, and 7. This will add up to 14, which is 8 plus 7 over 14, which is 15 over 14, which is like 1.07. Not going to box that in. Whoops. The coordinate would be 3.79 meters, 0.07 meters. Cool. So yeah, it would be somewhere right about here is the center of mass. Just about. Let's keep going. We have three identical sticks of length L, and they're all identical. So let's just say mass M. They all have mass M, and we want to figure out where is the center of mass. And we'll do the same thing we just did. This is, we have three objects here, so M1 x1 plus M2 x2 plus M3 x3, M1 plus M2 plus M3. Cool. We need a coordinate system. We'll make this our x-axis, we'll make this our y-axis, and this is our origin here. Make 0, and this will be 0. Okay. So the mass 1 is just M. Um, it's this stick up here. The center of mass of this thing is, we're looking at the x-axis here. It's half the length of the stick, which is L over 2. So do L, yeah, let's do it like this. ML over 2 plus mass of the second stick, but it's at 0. And then finally, the third stick, M, it's the same as the first one. So the length is L and the center of mass is L over 2. All over M plus M plus M, that's 3M. So what's ML over 2 plus ML over 2? That's just ML. And then over 3M, the M's cancel. The x coordinate for the center of mass is L over 3. So, somewhere over here. Okay. And let's figure out the y coordinate. Do that over here. That's M1 y1 plus M2 y2 plus M3 y3 over this. So it's M. Now the y coordinate for the first stick is just L. The y coordinate for the second stick is L over 2. And the coordinate for the last one, this is M times 0. All over 3M. So ML plus ML over 2, that's 3ML over 2 over 3M. The 3's will cancel, the M will cancel. And put the equal sign here. So we'll say that the y coordinate is L over 2. So this would be L over 3, L over 2. So L over 3 is somewhere about here. And then L over 2 is halfway. So maybe about right there. And so that's the center of mass for these three objects. And of course, the center of mass doesn't have to be inside any object. It can be outside. Cool. Let's continue. Okay. Now this is about center of mass velocity. For situations in which linear momentum is conserved, so situations like these that we've done before, um, in which linear momentum is conserved, the center of mass velocity remains constant. So, you know, here's two objects. The center of mass would be somewhere about here. I'm just kind of eyeballing it. And these two objects are approaching each other. The center of mass of these two objects also has a velocity. It's called the center of mass velocity. And if linear momentum is conserved, like down here it is, then that velocity stays constant. And we're going to show that. So I guess what we'll do is first we'll figure out V1F and V2F. We'll figure out those, the final velocities of the two objects. Then we'll figure out the center of mass velocity initially, and we'll figure out the center of mass velocity final and just verify that they are indeed equal. So we're given the situation here, we can solve this. We have the two masses, we have the initial velocities, we have two unknowns, but we'll deal with that. With two unknowns, you'll need two equations. But we'll start with linear momentum. This equation is not given on the formula sheet. You should memorize it. Cool. So mass 1 V1I plus mass 2. Now V2I is 1 to the left, so that's -1. Mass 1 V1F plus mass 2 is 2 V2F. Now, one equation, again, two unknowns. We're given, though, that this is an elastic collision. And when it's elastic, okay, that means that the kinetic energy is conserved, but it also means that V1 initial minus V2 initial is equal to V2 final minus V1 final. This is approach velocity and, or excuse me, the rate of approach and the rate of separation. Cool. So V1I is 5, V2I is -1, and we don't know these. So this is 6 equals V2F minus V1F. As we usually do here, we're going to set up a relationship. V2F equals 6 minus 6 plus V1F. And we're going to substitute this over here. But let's clean this up real quick. This is 15 plus -2 is 13. And we'll substitute 6 plus V1F for V2F here. 6 plus. And don't forget to distribute. That's 12 plus 2 V1F. Let's combine like terms. This is 1 equals 5 V1F. We'll divide by 5. And of course, that is 0.2. 1 over 5 is, yeah, 0.2 meters per second. To the right is V1F. If you can hear my washer going off over there. Cool. We'll plug that number over here, and 6 plus 0.2 V2F is 6.2 meters per second to the right. So after the collision, these objects are moving to the right. So my guess is that their center of mass is also moving to the right. Not really a guess. Let's figure out the center of mass velocity initial. which will be, I didn't even show the equation. The equation's up here. The center of mass velocity is m1 v1 plus m2 v2. You can keep going, and then over m1 plus m2, for however many objects you have. So for the initial, this would be m1 v1I plus m2 v2I over m1 plus m2. Cool. So that is mass one was 3, I think. Initial velocity was 5. Mass 2 is 2. Its initial velocity was -1 over 3 plus 2. That's 5. That's 15. That's 13 over 5, which is 2.6 meters per second to the right. Mhm. Cool. Let's do center of mass velocity final. That's m1 v1 final plus m2 v2 final over m1 plus m2. Mass 1 is 3. I think this was zero point 0.2. Mhm. And the other one was 6.2 over 5. Okay, that's zero point 0.6 plus 12.4 over 5, which is 13 over 5, which indeed it did stay constant. Cool. Oh, that's it. That's center of mass and center of mass velocity.